Right, so we're happy to have Marten Reehorst, who's going to talk now about Bootstrap, conformal Bootstrap again, but now for condensed matter.
Thank you, and thank you for giving me this opportunity to talk about my work. And thanks to the audience for being here, especially since there are these competitive alternatives available. I'll be talking about bootstrapping frustrated magnets. This is work together with Benoit Surat, both Van Rees and Slavorichkov. So I'll explain what frustrated magnets are, what the interesting open question about frustrated magnets is. There is some controversy, and I will explain how, using numerical formal bootstrap, I'm going to resolve this. And maybe, since this is called Eurostrings and this is purely condensed matter, I'll say some words on how it relates to a very similar problem in high energy physics in the conformal window of QCD. So what is a frustrated magnet? Now we all know what a magnet is. So if you have a simple antiferric magnet, for example, and you put it on a cubic lattice, then you will see that there's this ordered phase where neighboring spins are pointing in the opposite direction of each other. But there's also some magnets that show slightly more complicated structure because there's some obstruction to such collinearity. And so the simplest example is just if you take the same spin model that you already know, but now you put it on a triangular lattice. You immediately see you can start with pointing one guy up. If you would point his neighbor down, then the other neighbor can't be anti-aligned with both. And this, you can consider this as a nice theoretical exercise, but also this exact structure is importantly realized in many materials with names that I'm definitely not even going to try to pronounce. So yeah, just for concreteness, I'm talking about three-dimensional materials. So how do you get that, for example, because just now I showed a two-dimensional triangular lattice. So you get this kind of frustration just by putting different layers. If you have different layers of a triangular lattice where you have some antiferromagnetic interaction, and you have some interaction between the different layers, can be ferromagnetic or antiferromagnetic, that doesn't matter for the critical modes. So you can take this model, and again, this is a very accurate model of describing various materials that are realized in nature. Now there's a standard procedure to describe the critical phenomena of such a system, and that's to write the Landau-Ginzburg-Wilson effective action. And well, it's just like you would do it for normal magnets, but you get some slightly more complicated structure also in the momentum space due to this triangular lattice and this frustration. And so you get an order parameter that transforms as either a bifundamental of O2 cross O2 if the spins are constricted to live on the plane, or O3 cross O2 if the spins are free to move in 3 dimensions. You can also write a quantum field theory to describe the critical modes. So this has been worked out a long time ago that you can take a continuum limit, and this quantum field theory will, the fixed points of this quantum field theory will describe your critical phenomena. Here phi is an n-component complex field.
So is there an easy way to map the two coupling constants there and the two couplings in the lattice version?
I mean, no, not really. It's not like that, but so the answer is no. For example, the interaction between the planes doesn't even matter. If in the RG it will go away. So there's no such direct map. Yeah. So here you have one coupling that is that preserves a bigger symmetry, actually O2n. So there will be one okay, and you have one term that breaks this down to this ON cross O2 symmetry, the last term. So anyway, when you have these kind of phase transitions and critical phenomena and you want to study these, there's many different approaches that you can take. So you can take your actual piece of magnet and you can heat it and measure thermodynamic quantities. You can measure magnetic susceptibility. You can measure the specific heat, and you'll see that, for example, if there is a second order phase transition, then these thermodynamic quantities should behave as they should scale with the distance to the critical point to some power, some critical exponent. You can do renormalization group. You can take this quantum field theory and you write the quantum field theory, look for its fixed points. You can look at the characteristics of the fixed points, the symmetries that you have there, and the critical exponents that you have there, and make a prediction that way. You can take the system I just described, and you can do Monte Carlo simulations. Or you can take a different approach, sort of orthogonal to all of this, where you just say, well, I know it has to be described if it's a second order phase transition by conformal field theory. And conformal invariance offers a very rigid structure. Can I just identify the CFT just axiomatically from the consistency conditions of the CFT? And that's, of course, the conformal bootstrap. Now, if you do this for the simplest magnets, you do this for the Ising model, all these methods will give you the same. All these methods, if it's really greedy, they'll all give you the same answer. Bootstrap might give you one more digit, but in the end, it's just a quantitative difference whether you get one more. Everything agrees. But there's actually a kind of a more important open question when you consider these frustrated magnets. The bootstrap has a more important role to play rather than just give one extra digit. Because, oh sorry, there's a question.
Were the fixed points strongly coupled?
Yes. Yeah. So for example, you will study it in epsilon expansion, and you will go to epsilon equals 1 to get the three-dimensional case, which will be the strong copy. So for the first-rate magnets, there's disagreement, there's controversy, and I will explain how the conformal bootstrap can resolve this. But first, okay, what is the disagreement? So first of all, the experimentalists aren't in agreement. So different groups claim different results. Some groups say that the transition is second order. Some say that it's first order. Of the different studies that claim that there is a second order phase transition, they report different critical exponents that should be universally the same numbers, but somehow they are measuring different exponents. And also, they report critical exponents. You have different thermodynamic quantities that show different critical exponents, but they should be related by RG scaling relations. And there are critical exponents being reported that don't obey these RG scaling relations. You can also look at theory.
Okay, can I ask you something very stupid?
Yes.
I don't remember last time I set foot in the lab. So how do they actually do this sort of stuff? They measure stuff at different temperature and they plot?
Yes.
Okay.
Yes.
And the different groups reach different agreements?
Yes. So in the end, there is some. In the end, I think it's about fitting something. You have some function and you decide what kind of behavior it is, how you should fit it, and then you fit it and you read of numbers. And of course, there's always some ambiguity in it depends on how good your data is, but yeah. So there can be problems in fitting whether you decide that a certain critical exponent would be a good fit and it is a second order phase transition, or whether really it doesn't really look like certain critical behavior. So you can also look at what theory has to say about this. So for example, you could look at the epsilon expansion. But of course, then you're dealing with an asymptotic series at strong coupling. And it turns out that here also, there's different ways that you can handle this, different ways that you can do this, and they make different predictions. So let's just for simplicity first look at if you do the simple epsilon expansion, what is the picture? The picture is that if you consider the class of ON cross O2 symmetric theories, that for large n, this stable fixed point with the right symmetries O2 cross ON cross O2, it exists. But then for small n, it no longer exists. So let's look at the summary of different theoretical predictions. So I just was talking about this epsilon expansion, which is here the green line. So here we have the critical value of n, above which and to the left the fixed point exists, and below and to the right it does not, and this is as a function of d. So the epsilon expansion predicts something that depends again a bit on how you resum it, that at the most interesting point d equals 3, that there's a critical n just below 6, that below which the fixed point stops existing. But you also see some other lines. One is another method is called non-perturbative RG, and it qualitatively shows a similar behavior. But another way to deal with asymptotic series is that you first plug in epsilon equals 1, and then you resum the couplings and you look for the fixed points then. And if you do this for Ising or for ON models, this will give basically the same result as the other way of doing the epsilon expansion, where you first look for the fixed points and then plug in epsilon equals 1. But here, this is this black line, and it's a completely different behavior. Namely, it bends back, and it means that this extra area, very importantly, the area d equals 3, with n being 2 and 3, is now suddenly allowed. So now you have the question, could it be that actually there is this second, so in order for there to be a second order phase transition, this would have to be allowed. This fixed point would have to exist. So we want to answer this with a bootstrap, and this is a typical bootstrap question, because we can just ask the question, if it is second order phase transition, there has to exist a stable CFT with this appropriate symmetry, and we can test that using numerics. So I will be very short about the conformal bootstrap. You just use the consistent, so the actual method, a CFT has something called the operator product expansion. This means that you can take a product of two operators and replace it with a sum over single operators. And there's different ways that you can do this in correlation functions. If you have a 4-point function, which is the most studied in the numerical conformal bootstrap, you can, for example, take the first pair and the last pair, or you can take the first and third and the second and fourth. And this will give you two different sums that somehow have to work out to the same answer. And this gives you a very non-trivial consistency conditions called crossing equations. And these are hard to solve exactly, but we can numerically test certain assumptions. So concretely, what do we do in this case? Well, first, we know that for large n, this theory is supposed to exist. So a first obvious question is, like, can we find it? Can we identify in some space, this is the theory that we're looking for? And then just the question is this, can we just start lowering n and follow where this goes? And can we see where it stops suddenly? Well, the answer to both is yes. Otherwise, I would probably not be giving this talk. So here I show some island plots. You might have seen islands before. What's on the axis doesn't really matter. The important thing is that for the different fixed points that are involved in this problem, there's a very small O2n island in blue, and the islands that we're interested in here, the green one or the red one, the red one, is isolated from the others and from the O2n, and this means that we can follow this down and find the critical n. If we would start in the O2n island and we follow it down, then everything would be allowed because the O2n model exists for all positive n. So finally, what do we find? So here in blue I show the lower bound that we find where this island stops existing. So this is this is a rigorous lower bound on this critical n, and we see importantly that it shows none of this turnaround behavior, and very importantly, it's at d equals 3, it's well above 3, and so we show that this CFT doesn't exist, and therefore the phase transition has to be first order. I think it's 1 minute. Okay. Okay. If I have 1 minute, you could also ask, why does this CFT stop existing? And this is sort of understood that the expectation is that a fixed point stops existing because it collapses merges with another fixed point and then moves off in the complex plane, and so that at that point there's no real fixed point solution anymore, no real CFT. So if this happens, then it's also the expectation that CFT data approaches some special value as a square root of the distance to this critical value where this merger happens. And so you can look at some data, and again, it's not the most important what the data is, but the important thing is that we see very strong evidence of this square root behavior. And so not only do we see explain that this CFT stops existing, we also show that we find strong evidence that the way in which it stops existing is this merge annihilation scenario. Thank you.
Okay, so any questions?
I have a really basic
Okay.
what's happening at t equals 4? Like, why do we have an understanding of, oh, sorry.
So why
At
did
d equals
our
4?
line not start at d equals 4? Is that the question? Yeah, there's no
Yeah.
actually really good reason.
No, I'm just asking, like, why is NC 20 or whatever, like, do I understand what's happening, like, near d equals 4? Like, do I have, like, a perturbative understanding of, like, this collision between the stable and unstable?
So at n equals 4 exactly, it just becomes free. But I think that number is just, yeah, it's a number that you can compute, and I guess you can compute it exactly. It's a number. I don't think we understand why that number is meaningful, but yeah.
It's not quite continuous, the D2 coordinate, right? You use like, you do your epsilon expansion.
But even, like, near d equals 4, yeah. I mean, I don't care
One or
exactly.
two loops, you see some square roots, and you see some fixed points going off into the complex plane because the argument of the square root becoming negative. And that is one loop or two loops or whatever. That's where you see it, and that's what you use to estimate this. And clearly at d equals 4, right, the fixed point is just free. So then for all n, there's a
Okay.
Is it possible that there are fixed points that are not CFTs, so ones that have a conformal anomaly? Or
So so in general, a second order phase transition, we know it's scale invariant, and you expect that means that it also becomes conformal invariant. Of course, this hasn't actually been proven in D equals 3. I don't know whether that, yeah. So it's generally assumed that it's true that second order phase transition means scale invariance, and it's assumed scale invariance means CFT. Up to, there are some free counter examples, but
I guess you can. I mean, what's the terminology? Like, do you have like phase transitions where it's like the power of z is like not 1? So like, are those called like fixed points? I don't know. I guess they're almost fixed points, like Lifshitz scaling, for instance. So because you can have like real world phase transitions, which I guess are not really CFTs. They're like they break more symmetry.
Right.
All right, one more question.
Okay, it's not. Oh, okay, I just how come this has not been done before? It's a very interesting question. What has prevented people from doing this before?
Right. So there have been some attempts in sort of this direction to study it, but until recently, the tools numerically were just not available. So a few years ago, we developed with the same collaborators and more with Ning Su and David Simmons-Diffens, we developed a new technique to do the bootstrap. So it used to be that you would take a point and you would just test whether this would be allowed or disallowed. And in order to find, for example, such a tiny island as we have here, you would just do a grid where you roughly expect it and hope to find an allowed point. Then we developed this new method where instead, when you test the point, you don't just get the answer allowed or disallowed, you get a measure of success of how close you are to being allowed or disallowed. And importantly, this is a differentiable function. So we call this the navigator method. And it means that you can now, so you get a derivative that tells you, oh, I test some point somewhere, and instead of just saying disallowed, it tells me, hey, you should go that direction. And this allows us to very efficiently search larger spaces that previously would be impossible to search, and like find the boundaries of islands more efficiently. So yeah, we had to develop these new tools, basically also for this problem, motivated by this problem.
We're searching around the 4D space of 5D if you want to count, right? You have n in these free scaling dimensions, so doing like point by point sampling was going to be way too complicated. It's nice. This is a good illustration. But I think it's really cool that this conformal window, right, it disappears. This is sort of the first bootstrap result where you have really see the endpoints of the conformal window.
Well, pots.
Sure. Fine. But here, I don't know, like as not through this disappearing island without a lot of assumptions. I think that right, there's an island, the island becomes smaller and smaller, and both you can see. I think that's what you probably wanted to say about higher D as well. This method of disappearing islands, I think.
I didn't make any comments. Okay, no.
Okay, yes. Let's do go to the next speaker then.